Hi, I am Shantian, and I'm here to tell you about the work that I've been doing with the Advanced Energy and Power Program at University of California, Irvine, to determine the environmental trade-offs of energy storage systems in California. Let's start with an overview. Renewable energy such as wind and solar is a promising alternative to traditional fossil fuels due to their relatively low environmental impacts. However, a weakness of renewable resources is that they are intermittent. Energy storage systems are being developed then to address this weakness. Energy storage system can store electrical energy when the generation from renewable resources exceeds the electric load demand and release electricity when the demand is high and the renewable energy is not directly available. By doing so, energy storage system can shift the load to avoid curtailment of wind and solar generation, as well as release the tension of traditional power plants ramping. While the energy storage system can be environmentally beneficial by enabling large-scale integration of renewable resources, energy storage systems may have environmental impacts across their life cycles, including first, the sourcing of raw materials and the manufacturing and production phase of electric storage systems. And second, the implementation of the system through the use life. And third, the end of life of disposal or reuse of the system. Previous studies have indicated that implementation of grid-scale energy storage system could bring environmental benefits through increasing the use of renewable generation. The most studies in the field of renewable integration have focused on determining how much energy storage is required to provide operational benefits to reach environmental goals. However, as more energy storage capacity is deployed, the grid benefits and associated life cycle environmental impacts may scale at different rates. So here comes my research. My goal is to understand and maximize the net benefit of electric storage system usage. My research could be explained by this A plus B method as well. So for A, I try to use the dynamic electric grid modeling developed by APAP to capture the environmental benefit of implementing the energy storage system. With the increase of energy storage system, the curtailment of renewable energy decreases, so does the natural gas usage, which induces the reduction of greenhouse emissions. So the rate of the benefit change with the increase of energy capacity. It looks like this. With the first uptick of energy storage system, this will bring the biggest benefit. So that's the rate of the curve. With more energy capacity installed in the grid, the share of excess renewable energy that the energy storage can uptake reduces. This flats the benefit curve. Now from the B side, the life cycle impacts is captured by life cycle assessments of the energy storage systems. In this case, vanadium full battery is used as an example because the electrolytes of full batteries are stored in the tank outside of the stack. So the power capacity and the energy capacity are separated in the full battery system. So when this battery is scaled up to different energy to power ratios, the parts that related with power capacity and the parts that related with energy capacity are scaled separately. So in this graph, when the power capacity is fixed at 24 gigawatt, the impact of the production and use phase is increased linearly based on our assumption. the results of combining these two curves together is that the net benefit of the energy storage is maximized when the two impacts are balanced. The net benefit is equal to the benefit minus the environmental impacts associated with the production and use phase. So you can see the net benefit behaves like this figure 1 here. At first, the net benefit increase with the energy capacity increase until the point where the speed of energy consumption increase from the production and use phase caught up with the speed of the benefit increases, which leads to this maximum point of net benefit. If we keep increasing the amount of energy capacity, it will reach a point where the emission of producing the system can be larger than the benefit that the overall system can bring to the grid. So if the energy capacity that you installed on the grid exceeds this point, the energy capacity system will not be beneficial to the electric grid and the environment. And for different indicators, the thresholds may have different values. For example, in this case, for greenhouse emissions, the energy capacity is 224 in order to reach the maximum benefit, but for particulate matter, it only needs 128 gigawatt hours of energy capacity. So that's the capacity of the zero benefit point. So as I mentioned before, the power and energy capacity of 4 batteries can be expanded separately, which provide us an opportunity to explore the sensitivity of net reduction in greenhouse emissions and particulate matters emissions to both energy and power capacity. As shown in the figure 2 here, the black contours represents the combination of energy and power capacities where the net benefits reaches 0, and the green circle indicates the capacity combination that maximize the net emission reductions. So this black contour is the line that you don't want to exist, so that the net benefit will be negative around this area. And this green circle also shows that the greatest net reduction corresponding to energy capacity will diminish beyond this area. So the net reduction in emissions are largest at power capacity around 60 gigawatt for greenhouse emissions and 50 to 60 to 70 gigawatt for particulate matter, which corresponded to around 40 to 50 of the available generation capacity. And meanwhile, the greatest net reduction corresponding to energy capacity of 350 to 500 gigawatt hour for greenhouse emissions, and for 250 to 480 gigawatt hour for particulate matter, which corresponding to around 40 to 70% of mean daily renewable generation respectively. So in conclusion, by combining the dynamic electric grid simulation tools and the life cycle assessment tools, we are able to explore the potential for life cycle impacts to substantially diminish or even outweigh the environmental benefits of deploying energy storage technologies. So this study suggests that it is important to analyze trade-offs when transitioning to electricity systems with highly renewable penetrations that energy storage system must be sized such that net environmental benefits are maximized. And thank you for your attention. And please feel free to contact me if you have any questions or comments. Thank you.